So usually means that we want function that takes an object and assigns or not a class. And this is the simplest variant, the single class classification. So technically it amounts to saying that we have an object and we are assigning a 0 or a 1 to it, where 1 means that an object has certain characteristics and 0 means it doesn't. So, for example, Professor Kwasnicka here takes carrying a project that does single class classification, for example, to understand whether there's a cancer or not in a picture. So it's one example. Another one would be for the purpose of the seminar. We have a photo, and we are saying that there's a 1. The photo contains a row, and 0 other ones. So this is the single label case. Then we can have a situation where we have a set of mutually exclusive classes, and we want to assign one of such classes. So instead of just choosing whether a class is assigned or not, we want to say which one of the k classes should be assigned. As an example, we can think of the model of the Polish road classes. So instead of having just trying to understand the simple function, which doesn't mean the problem is simple, because just the fact that we assign 0 or 1 does not mean that the problem itself is really simple. So, for example, we have 5 classes of roads in Poland. So the photo contains a by road, a village road, a local road, next way, or a highway. And we can think that, okay, we have a data set where a photo can contain only 1, so those are mutually exclusive, and we are trying to build a function f that tries to be as competent as it can based on a certain training data set. So it's important because now those are the the cases of the single label classification. And what I'm doing is multi-label classification, which is, in terms of the size of the label space, a lot more complicated. So it starts with defining a label space, say L, and it contains labels L1 to Lm. So we have a set of labels, and we do not assume that they are mutually exclusive. So what we want to do is we want to attach or assign subsets of the label set to the object. So we have to the L, or the power set of L as the output space, which is technically complicated because we are getting an exponentially larger label space, because we can represent 2 to the L as a subset, as a set of subsets. So it's L, which are as elements that are subsets of L, or we can think about this as vectors A1 to AM, such that AI is in 0, 1. And you can see that it's actually, so for 1 it's a large label space, so we need a more rich or more sophisticated training set to be able to say something about this. And in terms of the output space, and on the other hand, we can represent it very differently. To give you an example, a function f that we could want to learn could look like this. It would be a 1, 0, 0, 0, 1, 1, 1. Let's say 1, 1, 1. It's basically assigning codes. You can actually code the subset any way you want. So if a photo contains, and in this case we see that as long as they are exclusive, we are close to a single, to a multi-class classification problem, single label multi-class classification problem. So let's say that 1 on the first position is connected to having a viral, if we have 1 on the second position, then the photo has a highway. If we have 1 on the third position, the photo has a sheep. And we have 1 on the fourth position, the photo has a farmer. So you can see that such a combination, viral, sheep, and farmer, is a reasonable one. Probably a combination highway and sheep is a less reasonable one. But if highway and a farmer is still possible. We can see that for 1 we have a lot of combinations, and that's a problem. On the other hand, we have what I said, a large label space. Some of the labels will be mutually exclusive inside the label space because it's logical to find sheep on the highway. And what is probably very important later is that some labels occur much more, or some label combinations occur much more often than others, because we are observing the data set, we do not have access to the clear phenomenon, so we are just observing the data set, and some events are more observable than others. Which means that we have a non-uniform distribution of label combinations, and that leads us to having a skewed or badly fitted model. And all of these facts actually occur together, making the problem even harder. So, going back to multi-label classification, multi-label classification is performed in 2 ways, usually. So, on one side we can use, we can adapt a method. And for example, those can be decision trees where when we are using on each node, we are using the data about all labels to decide whether to break or not. We have or using some or using entropy calculated over all labels, as in the multi-label adaptation of C4.5 method. And on the other hand, we have the problem transformation approach. Which is probably more, which takes the idea that we should transform the multi-label classification into a family of single class, into a family of single label classifications, either single class or multi-class. To look at this, we must see that there are 2 approaches that are on 2 sides, two completely antagonistic approaches to the problem. So one of them would be assume label independence, conditional label independence. And we would have, say, lambda 1, 2, lambda m, or L, for reasons of maintaining the notation, and we have some data. Maybe let's make it a small matrix. It's 1 to extend. And we could say that we have m, because we have m labels, that we have m single label, single class problems, that whether the label L1 is assigned is the first problem, whether L2 is assigned is the second problem, and the mth problem is whether Lm is assigned. So what we are actually doing is we are constructing m single label, single class problems. So we are learning fi from 1 to m functions, and our final function f of x is just a cross product of f1 of x cross fm of x. So this is one approach. We have reduced it to the first version of the single label, single class specification. And another assumption is that we can assume that each label combination or unique label combination represents how would they say it? A well-differentiated subphenomenon. So if let's look again at a matrix like this, the 2m x1 xn. So now we would say that if we have, for example, 1, 0, 1 here, then we have 0, 1, 0, 0 here, then such a combination, such a unique combination, is actually a case entirely of its own. Like that, we say that we could assume that on the input side, it should be so differentiated from the other inputs that we want to treat it as a class and treat all the unique combinations as separate classes that are mutually exclusive. So what we are doing is that we are turning it into one single label, multi-class classification problem with m mutually exclusive classes. Not m, sorry.
2 to the power
Let's say k, because it's not easy to determine the number of, well, it's easy because it's 2 to the m, but that's the idea. Well, we don't have 2 to the m unique label cases in our training set. What we have is that we have some observable portion of it. So if we, at best, we should assume that it's 2 to the n. But for now, let's say k, and in the next section I will tell you more about it. So what we have is we are training a function f. So we have actually two functions. We are building a function that converts a label set to the label set to label combination to set 1 to k to the set of classes. And then we are building a function g that learns or we learn a function g for that problem. And then our function f of x, original function is c2 minus 1 because this is a surjection. So this is it fills out of the entire data set and it's reversible. We classify inside the multi-class problem and then we convert back to the multi-label problem. And this has a lot of problems with this. So for one, we have the underfitting. So if we don't have to do the combinations in our training data set, that means we are assigning 0 to the combinations that are not happening in the training data set, which is a very serious underfitting, especially given that our training sets are usually small. On the other hand, due to the skewed distribution of label combinations and the very few combinations occurring most of the time, we can actually overfit the model because of this of fitting to the most present or most prevalent cases, and this So this is the problem with the second approach. The problem with the first approach is that we can actually have a false positive error in a situation where we have two labels that are mutually exclusive, and that's a big problem in outputs. And on the other hand, we might actually come across a combination that is completely improbable, not just mutually exclusive, but improbable because it doesn't happen. So that's the problem with the approach number one. And actually those two approaches are connected to the risk function that I talked about. Lemczynski and others showed that actually choosing this function determines which approach is better than other, because on one hand we can use a measure such as Hamming loss, which checks whether we have matched individual labels. So the Hamming loss is usually divided. It's an average over all observations for each object. We want to know whether for each label Li in L, whether we've matched the root. Okay, maybe I should write on the other. So we can have two classes of two major classes of risk functions. So of what we want to generalize from the data. So one is the Hamming loss, which average over all observations, and for each label it checks whether we've matched the label to the ground truth. So let's say, so this is supervised learning, so we know the ground truth. Li. So you can see that this actually that this measure actually sums the corners first. So it actually depends on the marginal probabilities of the output label space. So what we are working on here is that, and this is what Lemczynski showed, that to maximize this, we have to use the maximum marginal probabilities. So we actually look on the distribution of the output space. On this side, we can have the 0-1 subset accuracy, which is actually a measure that checks for each observation whether the entire set has been matched. So it's whether the entire set has been matched to the ground truth. And the difference is important because here if we've managed to match 3 out of 4 correct labels, we still get a score. Here if we manage 3 instead of 4, we don't. So this is completely dependent on the conditional probability of how the labels are distributed given the input objects. And this is basically what we're going through here, because we're going through rows. So we're going through each object fitting computations as different phenomena. Okay, so it is in general impossible to maximize the two of them at once. But we can ask ourselves about some approaches that actually can fix this, because on the other hand we have an underfitting, on the other side we have logical errors in classification. So none of these distant ends of the classification approach spectrums make sense. So the answer, the approach that has been applied since 2005 is to divide the label space and try to classify in label subspaces, because the argument is as follows. For one label subspace, we'll have a smaller number of labels, so a smaller number of combinations. So for example, if we have 3 labels, we have 8 possible combinations. So it's a small label space, we can have more observations following a certain group, evidencing this, the existence or non-existence of certain communication of certain combinations. And so a smaller output space should be easy to classify with, and then we have to get an intelligent way of merging them. And we probably should also have an intelligent way of dividing the label space. So I've taken up the problem of dividing the label space, mostly because it was done up until 2011. There was no modern solution, because the only established solution was actually doing random subspacing of labels, or random subsetting of labels, and it was actually a very elegantly described paper where the author forgot to mention that he's actually trying brute force on the label space. So to look at, there are three aspects concerning this. So for one, division, and we can have a partition of the label space, or we can have an overlapping division. So this is by now this is practically unresearched for multi-label classification. Dr. Igor Podolak from the Jagielloński University wrote a very nice monograph about this in multi-class communication, in multi-class classification, and partitioning has been tackled somewhat. But this one of the reasons that overlapping community detection is something that has been present in the literature for the last 3 years or something. So it's still something new. So this is, then we have the classification scheme, and it can be flat or it can be hierarchical. So imagine if it's hierarchical, then we have a first classifier G that classifies into group 1 to group, let's say, S, and then we have another set of hierarchical classifiers, of subclassifiers that decide which labels from the group 1 to apply, which labels from the group S to apply to a given X. And then we have some method of joining this together, and then we have the final output. So we are performing two levels of classification. And in the flat version, we are just doing this. So we are assuming that we have a division. We are training a classifier per group. And so this is flat. This would be hierarchical. And so those are the two approaches. And it's actually still unclear whether one is more preferred than the other. And the third aspect of the problem is that it's a division method. And up to date, there are two methods that are present in the literature. One is random, and the other is k-means. So what is actually done is that we are treating each of this as a vector, and we are running the k-means classifier, then the k-means classical algorithm on it. So I don't like the random one for obvious reasons. I don't like k-means because it requires a k. And so I decided that I want a method that does not require additional parameters, because this is supervised learning, so we shouldn't have the need to give parameters to the method. We have the training data for this. So here's my approach. So for one, let's take the set D, which is the training set. So we have an L, which is the label set. So let's construct a graph or a network. Let this be an empirical graph. So we have, let the vertices be the labels, and the edges, I will define the following. Maybe I should change it. So the edges are defined as following. We observe edges. So if Li and Lj are connected, if there exists an observation which has been labeled by the two of them simultaneously in the training data set. So in this representation, or that in the positions I and j in the output vector in the training data set, there are ones on both positions. Then this is how we construct it. And we can also add a weighted function to the edges. So we can say that this is the number of edges, and a number of objects labeled with both Li and Lj divided by the total number of objects. So this is practically the probability that Li, Lj co-occur given the training data set D. So this is the reasoning for constructing a graph. So basically the idea is that if we have a graph that is weighted and the weights are proportional to the probability that the two labels are connected, then if we find the communities, we should have the communities should consist of labels that are most probable to co-occur. So we need to get a method that does that. So that's actually the final point of the presentation. So what is knowledge? The knowledge in the training data set means that there's a certain structure of labels occurring together, and this structure should not be random. That's why it's knowledge. If it's random, that's just noise. And so what we want to have is to be able to select communities in such a way that they are as far as possible from a noise, from occurring if we had noise in the training set instead of the structure. So we would actually have, let's say we have a graph and that it's connected like this. So what would be randomness? Randomness would mean that, let's say we cut an edge in half, that we cut all edges in half, and we just connect them back with a uniform distribution. So we have complete randomness of how edges are connected. So if we have two vertices V and W, the probability that V and W are connected, in a random rendering of the observed graph, because we are following the degrees from the observed graph, is the number of edges that come out from V, from the degree of V, divided by all possible combinations, and that is the sum of all degrees, and sum of all degrees is twice the number of edges, as we remember from graph theory. So we have, and because we are doing this independently, so we have the same value for the second vertex. So we basically know how this is the random model. This is the probability that the two will be connected in the random variant of the model. And now, having this and having a community C, let's see be a set of detected communities. So let's see be one of the divisions of the vertex set. Then, if we define a random variable on a graph, it says it is equivalent to saying that vertex U and vertex tau are connected in the same community. So this is graph and community division, because it depends both on the graph and not on the community division that we are evaluating. So Newman, because all of this I'm speaking of is actually following Newman's paper in social networks and community detection. So we can define a modularity measure Q on a set of communities, which is an average case of X U V being connected in the observed graph. So we know the graph we built on a training set, the graph that represents our knowledge, observed knowledge, minus the average connectedness inside the same community of the randomized version of the graph. So let's say that this is a randomized version of the graph. Randomized as set here, which basically amounts to saying that we are summing over all pairs of vertices, and so this is actually the probability of UV being connected in G in our observed version. So we basically look at how many edges come from U and V in our graph. Yeah, Emily, I'm here. Minus the probability that they are connected, that U, V are connected in a random variation of the graph. And having this method, we know what we want to optimize. We would like to find for our graph, for the graph that is representing the coherence, the label coherence in the training data set, we would like to have the division that gives a maximum Q. So we want to have the division that gives maximum modularity. And that's basically the N. So a couple of favorites. So this is actually NP-hard. And it's NP-hard because of many reasons. One of them is that it's connected to a Potts problem in physics, or the spin glass problem in physics. It turns out that the same structure goes on there. The good thing is that we have a variety of algorithms that can tackle the problem, from greedy ones to matrix ones. Turns out that you can actually take leading eigenvectors of the matrix and you are getting a good approximation. And it can be done relatively fast comparing to, it's actually faster than k-means. So that's and you don't have to test the parameters, and you don't have to select the k, you do not have to reinitialize. So the method works very well, and it's the established standard in social networks. And in our first set of results, it basically gave better. It gave better results than most other methods, or comparable results to other methods, but in 1/5 of the time. So it's actually really a nice improvement. There are still some details we have to come up with, but this is the general idea. Thank you.
So let us start discussion now. It's clear for you what is the subject of this PhD?
For me, it's not really clear what is your part and what was the previous works. So I don't see the division where is the line.
So the previous works.
What is your contribution?
So my solution is that I'm trying to apply methods for complex networks. So these ones, yeah.
But there are methods developed originally for social networks, yes?
Yes.
Would you like to adapt this method or take directly?
So I'm trying to adapt them. So for one, it's not really that easy to take them directly, because you still have to make a choice whether you want an overlapping version or not, and whether flat or hierarchical approach is better, and actually which approximation method is the correct one against against the multi-label problem. But mostly I'm trying modularity, yes.
Okay, but for me it's not clear because usually mapping level classification, you have a data in such a form that every object is given as a vector.
Yes, the input space.
Okay, and you have a number of, let us say, number of labels. You have a subset of labels. It's given by 0, 1 in a given place, it doesn't matter. And in your approach, it seemed to me that you don't use this.
Yeah, that's the idea.
Yes, so you lost a lot of information. It could be good or bad. I don't evaluate it now. But you use only that one object, it doesn't matter, one, two, doesn't matter, has such a subset of labels. The second object is in given test labels. So, really saying your input data in a training set is in the form object given as a number, doesn't matter, and set of labels assigned to this object. So you don't require your object is given by a set of the same attributes as normally classification task, normally every classification. Yes, so you forgot about this part. You have only a given object. It could be only by the number, it doesn't matter.
But it's only in the for the label space division. Then if I'm doing the classification, I'm putting the input space. I'm only using the output space for division.
So it's only, let us say, output division. It's a clusterization of that. Yes. So in such clusterization, a given label can be present in a number of clusters. Yes, so
or in one, it depends.
It depends, but you assume that it could be, so it's a special kind of classification of clusterization, which allow to assign a given object belonging to every class. Sometimes it's not. Okay, so now I think I understand.
So it's actually well accepted in the literature because for the division. Because the division adds an additional layer of time on the method. So the idea is to assume that the output space actually predicts some kind of differentiation in the input space. And this is of course a good question, and whether it is such, whether actually a data set has such a differentiation or not. But maximum modularity obtains some hinted, because if we have a very small modularity obtained on the graph, then perhaps the data set isn't actually far from being.
Is taken into account in the second or not? Directly not, but indirectly I think that it influences.
But it is because, so I didn't go into details, but we can replace the degrees with the strengths, so the sum of the input weights, and the number of edges with the total strength of the graph, and then it does. And I'm testing both variants, the unweighted and the weighted one, and comparing the results. Because this is also a question whether, because sometimes the smoothness will impact.
Do you have a question? Maybe you know? That's my question. A question? So, more questions? What do you think about this subject, the fullness of this subject, maybe this approach, and this way of presenting? Also. Please remember that you should define your main goal of your PhD thesis on the basis of the subject. If you know the main goal, maybe someone of you still is not sure about the main goal. Yes, because you are the second semester, so I hope that every one of you are at least the second semester, yes, the PhD study. I hope that every one of you has in your mind, imagination, what is the main goal. Maybe it will change doing the research. Yes, because it's inclusive. So sometimes we are not able to predict, but I hope that you have in your mind. So your main goal or your contribution is important here. And possible usefulness, if you are able to say about it. Yes? What is the practical possibility to use the result of your work? Maybe it's only theoretical, so you should say that it is only theoretical research. Yes? If you see some usefulness in real life problems, for example, so please indicate the such usefulness of your subject. Yes? So what do you think about such presentation with table? What is your opinion?
So if you're using a lot of maths, I think it's useful to use a blackboard. But if you are ending your PhD, so there is a presentation, so you can also use a blackboard, or that's not possible. So you have to have slides.
During the question and answering, you can use a blackboard. It doesn't matter. But during the presentation, usually not. Usually only the presentation slides. And I think that it is not from some because someone wants. It's time. If you have presented, you have written, you have done the pictures and slides, it consumes less time to present it. Yes? Such presentation, I think that it is very useful during the lectures. If you want to teach someone a given subject, yes, for example, the lectures with students, such an approach is very useful because the student have time to follow you, to understand you, and to think about what do you say, yes. But during the presentation, the results to the audience not deeply. If you don't want to deeply go into the subject, so it's better to have a presentation because it requires less time.
It's very hard to show results that way.
My results
you want to show results in order to have tables, or
especially your data set.
70. Also, I would like to add, on the one hand, it's better for students to understand it, and on the other hand, it's easier for presenter to make comments on every part of the equations. I think it's also beneficial for the students.
Because you show your thinking, your way of thinking.
While writing.
Yes, if you are writing, you show the students your way of thinking. So they can follow not only what are you writing on Blackboard, but what is your thinking.
Exactly.
So it's better. It's better. But it requires a lot of time, more time. So, but if we work with the student, we can think, what is the most important? To make a program or to teach student? It's not always the same. It's not always the same. I can say that usually it's not exactly the same. So you should have in your mind, what is the goal when you are in the lecture with the student? Yes? So my advice is try to teach student, not try to make a program. Yes? Teach the student, it means you must try to improve their skill of analyzing, thinking, understanding. Because it's a problem with the student. I think that every one of you, if you have a lecture with the student, you see it. And analyzing, thinking is not a good thing for them. Yes? So because from the basic school, there are tests. You don't have time to think during the exam. You must test. You feel test. It's very, very bad. And I saw a paper of American psychologists that it's time to go out from tests at school and universities, because the society is not, I can say it's more stupid than in the old way of teaching. Yes, so I saw at least 2 or 3 such papers now. But if you know the test will come into Europe from United States, because it must be not how to say, objective, not subjective but objective. Yes? Tests are, doesn't matter what are you thinking. So tests can be evaluated by administrative workers in the United States, in the 2 universities where I have colleagues. They give a test to the administrative workers, and he is present at the beginning, so the student can ask about some understanding of the question. So it's a very short time, and he has to go out from the room. So it's objective. Of course, objective. Everyone can evaluate in the same way. Me, you, and you. Yes? But if it is good, my opinion is not.
There's also a good result on teaching using slides that we usually teach with the light students. They have a negative impact on
at our university, it is obvious to give students some part of some help material for the lectures, usually it's a slides. It's obvious. So I'm preparing the slides, but in this year I will try to make less information on slides, but I don't have time enough to make these slides in such a way, because students use these slides as a textbooks, but it is not a textbook, yes? But I try to use in different ways slides sometimes. Sometimes it's a very difficult part of material, so I use slides. But I am trying to open the slides and to discuss with the students, to present with blackboard, and close to the end, I show the slides and maybe I forgot something, so it's maybe something interesting on these slides. So I prefer such lecture, but some part of material can be such difficult that it is difficult to, for example, to think good exam. If you want to show students some special kind of the behavior of the method, you must have prepared well example. Yes, because for example you want to teach students some backtracking, but you give an exam without necessity to backtrack. Yes, so it's not good. So sometimes the exams could be given at the beginning, at least on slides. Yes, and you can solve with the students on blackboard. So this discussion not about the philosophy of teaching, but about the presentation today.
So maybe I can ask Wojtek and Łukasz, because they saw it the last time. Is it better than the last time?
Much better.
Yeah. It's more condensed, I think. It was a lot longer last time. And it was important.
If I could say, I think you could shorten the first part, because I think it was the easiest one and it was the longest one about classification.
Yeah,
I think most of us knows those things, so you could only give the symbols and explain them, maybe not write every definition.
Mm-hmm. So especially in this audience, because majority of this person here is familiar with classification tasks. Yes, with the basic classification task, I think that almost everyone is familiar. We have only one guest from outside our faculty of our computer science, because we don't have management students. So I think that only the idea for classification is important to him to understand next part. So I agree with his opinion that the beginning very simple was too long. It's my opinion. Okay. Thank you.
If I may, I would like to disagree with your opinion.
Yes, you can. Why not?
And that's because it's good when you, well, okay, we all know the subject of classification. It was slow, but still it's 5 p.m. and perhaps
We need this
before this meeting we had an entire day thinking about different things. So it was like, okay, let's sit down, let's remind ourselves about simple classification, and then we start with more faster material with new things. So I think it was a good start, and since Piotrek was right on time, he wasn't late with the finish, so I think it was acceptable.
Okay, maybe someone wants to say something. No? Why not?
Hi, question.
Yeah.
I'm not sure if I understood you correctly, but is your goal to divide the output space into two or
Into many.
Into many? Right. Okay.
But I know where you can get this idea from, because this method was originally designed to divide into two, then into two, then into two, because the generalization came to us a couple of years later. So I still have the sense of, when I'm talking about this, that I talk about it as if it was possibly divisible into two.
Yeah, I've asked because you showed the hierarchy consists of two, of just two edges, and I thought that you want to split it into just two.
No, I want to iterate over all edges, so I can have more splits. But
So I have one question, not about the way of presentation. What do you think about your approach if you have a very big set of papers? It means 1,000 or 20,000.
So the most important thing about, and actually why I chose this approach, is that the only non-linear part is the edge part. So that when we do for example, in the greedy method, it's linear in terms of vertices, but it's non-linear in terms of edges. And we usually have much less edges in bigger spaces, because we don't have so many examples for the data set.
But the frequency could be quite big, so still you can have a lot of subsets. And
But they will be very far from.
some subsets could be absent in the
Yes.
in such a problem. Yes.
It's still problem.
It's a data problem.
It is.
Yes.
It is a problem.
So it's the same problem with another approach.
So it's a little better because it's not as it selects the smaller subspaces. It can actually select subspaces that are not present as combinations in the original data set, especially in the overlapping case. So that gives a different output space when we build the subclassifiers. So for example, let's say that in such a graph, we can actually have this as a community if the weights are small here and here, but those do not occur together. So we can actually have a labeled space combination that doesn't happen in the training set.
Excuse me, Professor, we have 5 minutes to go before building.
See you next week. You have